All right, everyone. How is everyone? Desara, for example. You, how are you?
I'm good, thanks.
Are you in Istanbul?
Yes, I'm here.
How is the weather?
It's good today. Not that bad. Yesterday was
Quite bad.
worse. Yes.
Yeah.
How are you?
I'm fine. I'm stuck somewhere in North Aegean because of this weather, and we had terrible winds and gusts and so on. And there were so many warnings. There were 36 mornings between 8 in the morning and noon yesterday. And there were some pretty bad scenes we saw on TV.
That is so bad, yeah.
I decided not to come, but then later on at 9 p.m. or something, the president of the university has sent us a Twitter message, as if we are going to look at Twitter messages, but that's life. At hard times, it happens.
Yes.
You are from Albania also?
Yes, I'm from Albania.
Because I think we have like 10 students or so from Albania.
Yeah, in our class, this year we are 5.
5?
Yes, 5.
Okay.
5 people.
Okay. So today I made a Turkish introduction, but I was only for the Turks. I'm going to repeat the same thing. Today we are going to start AC analysis of BJT circuits. So it's going to be something like that. But before I start this, I would like to show everyone a video to sort of have an easy, after 2 weeks of having no classes. 1 week was midterm exam, 1 week was the break. So I'm going to show a video first, which I hope is going to make it a little easier for you. And I'm putting the link onto chat, and I will stop my video and start the YouTube video itself. So here we go. All right, can everyone hear me and hear the video? Let me do this again with share sound. Okay. All right. All right. Now everybody sees the load line, right?
Yeah, we can see.
Okay. This is a very nice channel in YouTube that has short but very informative videos. Is somebody writing from chat? Yes. Okay. Unfortunately, I will put it to the side, but I cannot see chat messages. So if you have any question, just basically interrupt me with your voice, because I have a small screen. This is a laptop. This is not like the big screen that I had to show the videos when we were doing sort of face-to-face. Anyway, here we go.
Hey there, welcome to another episode on the Electron X channel. I'm David Williams, and in this episode, I want to talk about AC load lines for BJT circuits. To start off with, I just want to refresh your memory about DC load lines. So let's assume that right here we've got a DC load line, and what this represents is the range of valid values for IC and VCE when we're looking at only the DC portion of a circuit like this right here. At one extreme of the load line over here is the saturation current, or IC sat. And this represents the maximum current that you can have in the collector. And that maximum current from a DC point of view is going to be this voltage, the VCC voltage across RC and RE. In saturation, we can assume that VCE is very low, as close to zero for an ideal amplifier. So this IC sat is going to be VCC over RC plus RE. At the other extreme of the load line is the point where the circuit is cut off, the current is cut off, and this is called VCE off. And this is the voltage across the collector and the emitter that will be needed to make sure there is no current in the collector here. And that's going to occur when the voltage across the collector emitter is equal to VCC. Now, the possible combination of values of IC and VCE are going to vary along this load line, and the way that they vary is by changing the base current into the transistor. And that base current, from a DC point of view, that base current can be adjusted by changing the values of RB1 and RB2 to bias the base at a certain value. Okay, I've redrawn a representation of the DC load line here, again with IC sat at the saturation current and VCE off at the cutoff point. And again, these are representing the DC values for the combinations of IC and VCE. The AC load line is related to the DC load line, but it represents the range of values of IC, in other words, the AC value of collector current, and VCE. In other words, the AC values of the collector emitter voltage. So from an AC point of view, we are no longer looking at a circuit like this because we don't need the DC source voltage. We are assuming that the capacitors are set so that they become shorts at the AC operating frequencies. And so we can represent the circuit in the AC model. So we will have a V-in that gets applied to some kind of input impedance, and then it comes into the transistor. And in the transistor, we have the base here, we have the emitter here, with a little RE value in the emitter, and then the collector, with the dependent current source representing the collector current. So this is the transistor, and then that gets applied across an output load. And this load resistor here, I'm going to designate it as little r load. And in the AC model, it's going to be equal to this resistor in parallel with the RC. So since we're dealing with the AC model, I'm going to get rid of this. So again, for the AC load line, we are concerned with the IC value and the VCE value. This is the collector here, so the VCE value is going to be the voltage across the collector and emitter. To get an understanding of what the AC load line is, let's go back to the DC load line here and assume that we are biased right in the middle of the DC load line. Here's our operating point, Q, and it has a value. The operating point of Q is VCEQ, which is half of VCE off, and here is ICQ, which is going to be half of IC sat. And then the AC load line represents how IC, the little IC, and VCE can change with respect to the Q operating point. So there's going to be a change of IC, and the relationship between that IC and VCE from looking at this circuit, IC is going to be equal to the voltage across this R load divided by the R load. And this IC represents the change in IC across the AC load line, and this value of VCE represents the change of VCE across the AC load line also. The reason
Now here, Brian, I want to emphasize at DC, we use these capital letters. At AC, we use small letters, and we call it small signal analysis, the AC analysis, okay? Now I continue, or the video continues.
The reason that the AC load line and the DC load line are different is because for the DC load line, what you're concerned with is RC and RE. Whereas for the AC load line, your load changes. Your load is now this R load that I'm designating here, which is going to be dependent on the actual load resistance and RC. But in this case, it's RC in parallel to R load. For the AC load line, again, we want to look at the two extremes. We want to know what the saturation current is from an AC point of view, what the cutoff voltage is from an AC point of view. The IC sat is going to occur when the transistor goes into saturation, and that's going to occur at ICQ plus whatever the change of IC is, which is equal to ICQ plus VCE over R load as I've indicated here. And since I know that our load, which is the external R load in parallel to RC, is going to be less than RC plus RE, I know that my IC sat is going to be greater than my DC saturation current. So on the graph here, my IC sat is going to appear somewhere above the DC saturation current. At the other end of the load line, I want to look at the VCE off. But first of all, I can look at this relationship between IC and VCE and just rewrite it in terms of VCE. And then considering my cutoff point from an AC point of view, designated as VCE off here, is going to be equal to the DC operating point plus the VCE swing going in this direction. So VC is going to be VCEQ plus the VCE swing, whatever that happens to be, or the delta VCE as due to the input AC signal.
So hereby, swing also means how the time-dependent signal changes.
Rewriting VCE in terms of IC and R load, we get this expression. And I can see that my IC, the amount that my collector current can change from the operating point, is going to be ICQ. It's going to be that amount there. So I can rewrite this again as VCEQ plus ICQ times R load. And again, since the R load is going to be, well, my R load is this expression, is going to be less than RC plus RE, I know that my VCE off from an AC point of view is going to be less than my DC cutoff voltage. And that means my VCE off, my AC VCE off, my AC cutoff voltage is going to be somewhere between the DC operating point and the DC cutoff voltage. All right, I've drawn the AC load line here approximately. It should pass through the Q point, but I didn't quite hit it. So the swing for the AC load line is from VCE off all the way up to IC sat. Now, what the AC load line tells you is what the maximum peak-to-peak output you can have for a circuit without clipping occurring. So if we are biased, remember we're going to be biased at the operating point here, I'm going to be able to swing down to here and swing up to here without clipping on those two sides. But if I'm swinging up this way, that's a little bit longer than swinging down this way towards cutoff. So what I have for my maximum peak-to-peak voltage would be the swing this way, or if I'm just looking at the VCE axis of the graph, I can swing from the VCE DC operating point up to the AC VCE off point, and that VCE off point is going to be equal to the DC collector emitter voltage operating point plus the DC collector current times R load. So it's this voltage here, this value here, which is going to indicate my maximum peak, and then 2 times that is going to be my maximum peak-to-peak voltage I can have without clipping. And this right here is the important takeaway for the AC load line, because we want to know what is the maximum output I can have before clipping occurs, because when clipping occurs, that means that the output signal, the output voltage, is no longer representative of the input voltage. I hope you learned a little bit about AC load lines, and watch the example video of AC load lines next to see an application of this AC load line. Thanks for watching, and I'll see you in the next one.
All right, so that was the short introduction. And now, whatever we're going to see, especially, I would like to emphasize this little, let me go back. Okay, there was this little thing that represents the BJT AC. We are going to learn today, or you are going to learn, where that originates from. So if you didn't understand it right now because you didn't have enough information, but once we start to watch, actually to go over my slides, which are these babies here, which I have already put onto Nineveh, and let me get my laser pointer, then things will make a little more sense. Okay, again, if you have any questions, please interrupt me because I cannot see chat on this little screen. I changed the settings. So we know now why these are called BJTs. It comes from the bi of the bipolar, and transresistor comes from the transresistor comes bipolar transistor. Why resistor? Because we know that always the emitter base junction is forward bias. However, base collector junction is reverse bias. So emitter base is always forward bias. Base collector is always with reverse bias. There comes the resistor. And now you know they come in actual form if they're discrete, like with these 3 pins, or looking at how the internal structure is, it's like that. But usually use symbolic representation like that, or these, and these 2N107 or 2N22E, these are the different types of transistors. And remember again, let's remember again, we have AC, DC voltages to bias them. So here it's between ground and 9 volts DC. And then we have some capacitors. These capacitors are designed, put in there to isolate this BJT circuit from AC sources or AC signals and to work only at DC. And these are called coupling capacitors. But if we have a capacitor over a resistor, these are called bridging capacitors. The coupling capacitors connects the circuit to the input signal and to the load. The bridging capacitor basically bridges all or part of the resistor connected to the emitter. And the reason for this is, as we will see, to increase the gain, the amplification. You remember the input-output characteristics? The output characteristics are family of curves. And for this class, for constant base currents, we have constant collector currents on this end. And these are as a result of different base currents. So if the base current is 10 microamps, the collector current is 1. If it's 40, it's 4. So from this, we can find beta is equal to 100. And we remember the modes of operation. But when we look at transistor as an amplifier, we are basically using it in the active mode. Emitter base forward biased, collector base reverse biased. And the input characteristic is basically the characteristic of the semiconductor diode. So let's look at the modes of operation. And you'll hopefully remember it from the video, the DC load line. And here we have the AC load line. And as you would see, the AC load line is slightly different and has a slightly different slope between the cutoff region and at the edge of saturation. And the active mode is in between them, and it has a negative slope, and it's usually pretty linear, close until it gets close to the edge of saturation or edge of cutoff. So in the AC mode, we still have the VCC and the ground, or VCC and minus VEE, but we have an AC source, small signal, and therefore it's indicated with a small v. That's comes as input into the base. All right, let's go on. There are some basic definitions. What is a DC signal? DC signal is a signal whose time average is non-zero. It could be plus minus 5 volts. And these little brackets, they indicate the time average over time. However, if we look at an AC signal is a time-varying signal like sinusoid or a cosine wave. And if we take the time average of it over several periods, it's 0. So this is an AC signal, and it has an amplitude and a wavelength or a frequency. What is the wavelength? Wavelength is the distance or the time from one upgoing sinus wave to the next upgoing sinus wave. So this is a wave. That's the wavelength. And the inverse of this wavelength, 1 over wavelength, gives us the frequency. And that is the amplitude from the ground level, either to the positive maximum or the negative maximum. But these two maxima are the same, so their absolute values are the same. There is no DC signal on this. And then signal sources. Well, in electronics or electricity, we have voltages and currents. So the AC signal sources also come as a voltage source, which is represented by the actual ideal voltage source with the internal resistance of the source in parallel. The current source is represented by the ideal current source in parallel. This was in series. That's in parallel with an internal resistance of the source. So the internal resistance of a voltage source is very small. The internal resistance of the current source is very large. Why? Because we want to amplify something very close to the actual signal source in voltages. So there will be some sort of resistance in the amplification stage, which we are also going to learn. And so that voltage is going to be voltage divided on the internal resistance and the internal resistance of the voltage source and the internal resistance of the amplifier. On the other side, in the current amplifiers, the internal source of the amplifier will come in parallel to this internal source of the current source. So that means in this node, the current is going to be divided into two sides, and we want most of the current to flow over the internal resistance of the amplifier. That means the internal resistance of the amplifier should be quite small in ideal form. So alternative current signals, they could be square wave, they could be sine wave, it could be several frequencies, and the time average is, of course, 0. The frequency is 1 over that wavelength. And frequency ranges for this class are limited from DC to about 20 kilohertz. Why 20 kilohertz? That's the audio range. And when we are all babies, we can hear pretty much up to about 16 to 20 kilohertz. But as we age, it goes down, and at really, old ages, it goes down probably to about 4 to 6 kilohertz. So we lose some of the sensitivity of our ears. The amplifiers are also represented symbolically different. They are represented by this triangle with 2 inputs and 2 outputs. And one of these inputs and the output pin might be grounded, but we talk about an input port and output port. They might be grounded, they might not be grounded. In that case, the amplifier itself has some sort of a connection to the ground, And since we are talking about biasing also, what is not shown here is the biasing power supplies, either VCC and minus VEE and the ground. So in general, the representation is like this. We have a source, then an amplifier, and whatever is amplified goes over to the load. And for example, this could be the little signals that the phone, for example, it could be the regular phone line, ground line, or it could be your cell phones. Whatever signal comes to your cell phone picked up is so small that it has to be amplified. It has to be demodulated also, but I'm not going to confuse you. That signal is amplified, and for you to hear it, you need a little loudspeaker. So this load represents that loudspeaker. And the transfer characteristic of a linear voltage amplifier is like this. So the output voltage versus input voltage, the relationship between them should be linear. So the gain formula, and since formula is not an English word, the plural of it is formulae. Like virus is, the plural is not viruses, is viri, or bacterium. The plural is, although the English use bacteries or bacteria, the actual bacterium plural is bacteria. Anyway, we have an input current going into the input port of the amplifier, an output current, the input voltage, and the output voltage that drops on that load resistor. Okay, how do we find gain? We could have a voltage gain, and that's basically the voltage, output voltage divided by the input voltage. We might have a current gain, that is output current divided by the input current. And sometimes they are represented in decibels. And so that would mean we take the absolute value of voltage or current gain, and why absolute, that will become clear towards the end of the second hour. We multiply it by 20, and then the gain units is in decibels. The voltage gain and current gain are unitless, or voltage divided by voltage, amperes divided by amperes, but in decibels, we indicate them in decibels. So current gain or voltage gain in decibels. And then if there's current gain and voltage gain, then there has to be a power gain. And so that's the load power, which is basically the output current multiplied by the output voltage divided by the input power. And that's basically input voltage divided multiplied by the input current. So when we look at these three formulae, then it's obvious we can also find power gain in decibels. So power gain is voltage gain multiplied by current gain, or power gain in decibels. And now we don't have the absolute value. Why don't we have the absolute value? Because power can never be negative. So remember that. Current might be negative, one of the currents. That means the direction of the current is negative, and as a result, the voltage might be negative. So power gain is current gain multiplied by the voltage gain. And when we look at the amplifier transfer characteristics, what is that? The input voltage in the x-axis and output voltage in the y-axis. We had something like this earlier here. Oops, here, you remember? That was shown very simply. Here, it's a little bit more complicated. And so if we have positive and negative biasing voltages, the output, whatever it is, after being amplified, can mathematically be over that plus VCC, or can mathematically be under the minus VEE, but physically it cannot, because the power supplies, or the range, as we say, is limited by these plus and minus power supplies. And we want this gain be very linear. Well, what sort of a meaning does it have? Let's see. We have an input voltage, and that's the one shown here. The input voltage is a sine wave that has a certain range, several maybe millivolts. And looking at the slope of the characteristic, we can basically find what the amplified voltage will look like. For example, here we start at 0, go up to this point. So the amplified voltage will also start from 0, go up to this point. And on the negative side, it will start again at 0. We'll go to the range. And that range, we find it here. However, if we have a very large input waveform, well, we start here, and that's the 0 point. And then it goes all the way up to here, but it's outside the input-output range. So it's basically can come physically up to this point. And at this point, without going over, it is clipped because it's saturated. So our input wave might be a sinusoidal waveform, but the output might look like a square wave. And this is actually how square wave generators are made. But for amplified signals, we don't want these clippings. And if we have not a negative power supply, but 0 to some range, then the whole analogy will be between 0 and that range. So we have to be, our operational point must be somewhere here. In this particular example, it was at 0. Any problems or questions here? I think it's obvious. Okay, so circuit model for amplifiers. Well, there are T forms or pi forms. And this is a pi form. So the input is between here, and the output is between here. And an amplifier in general, this is not BJT, this is a general amplifier, has an input resistance and an output resistance. And in this example, we're talking about voltage amplifiers. So the input voltage drops on this input resistance. The amplified voltage, AVO is the amplification. AVO-VI is output open circuit voltage amplification ratio, or the gain. AV0-VI is the amplified voltage, but this AV0-VI drops on the output resistance of the amplifier plus the load resistance. So from here comes the condition that this load resistance should be much more higher than the output resistance of the amplifier, or the amplifier's output resistance must be very, very small, so that most of the amplified voltage drops on this load. A similar thing happens at the input. The voltage source, the Thevenin equivalent, as I went over a little while ago, has its internal resistance. And unfortunately, we cannot change that internal resistance. So the input resistance of the amplifier should be at least 10 times larger than this, so that most of the input voltage drops on the internal resistance of the amplifier. So the voltage dividing ratio here is determined by Ri divided by Ri plus Rs. The voltage dividing here is determined by RL divided by RL divided plus, Rs. And so the total voltage gain, V0 divided by Vs, is determined by these two voltage dividing resistor terms plus the output open circuit gain of the amplifier. And in this class, we'll learn how to find that AVO, or output open circuit voltage gain. If we talk in general, there are 4 types of amplifiers. First, the very generic voltage amplifier. So it has an input resistance and output resistance and is symbolically shown like this. Then a current amplifier, again an internal resistance and an output resistance, but since this is a current amplifier, the output resistance comes in parallel and not in series. Or we might have a transconductance amplifier and transresistance, but to make things easier, I'm going to skip them right now. We'll go over them next week. So open circuit voltage gain, AV0, is then V0 divided by VI when there is no current, nothing is connected to the output. And it's either unitless or volts over volts. And as I talked about a little earlier, this voltage amplifier should have ideally infinite input resistance and 0 output resistance. When we look at the current amplifier, and here I need to show you the source types again to remember it. In the voltage amplifier, Rs comes in series with Ri. Therefore, Ri has to be very, very large. And R0, the output is going to be divided on these two resistors, R0 and R load. So R0 has to be very, very small, ideally 0. When we have a current amplifier, this current source is going to be connected to the input. So Ri comes in parallel with Rs. And we want most of the current to flow on this Ri. That means ideally Ri has to be 0 or very small. And the short circuit current gain is given by I0 divided by II when the output voltage is 0. So that means these two pins are connected or shorted. And it's either in amperes divided by amperes or unitless. And what about R0? Well, we amplified the current and we want most of the current to flow in this direction and go on to the load resistance. So therefore, the output resistance of the current amplifier has to be ideally infinity. If the voltage drop is the same on R0 and the load resistance, if R0 is, so that means the voltage drops are the same. If R0 is very large, most of the current will flow on RL. And so this condition is satisfied. The transconductance and transresistance, as I said, we'll go over them next week. But now, so far, we learned the ideal characteristics of voltage and current amplifiers. So what or how can we measure these input and output resistances or impedances? We can measure the input resistance by looking at the input voltage over here, dividing it by the input current. That is much easier than finding the output impedance. because to find the output impedance, we need to have a new source connected to the output. And all the dependent sources in here, now independent sources, if they are voltage sources, they should be shorted. If they are current sources, they should be opened. So this way, when we connect a voltage source to the output, we look at the voltage and we look at the current, and the output resistance is found that way. Sometimes in books, they call about impedances. And impedance is actually, as you know, impedance means there is not only a resistance, but also a capacitance. But for this class, we talk about resistors. Everything is real. In analog circuits or digital circuits, it might be different. So the small signal models. Well, small signal model for a bipolar junction transistor comes either in pi form or a T form. And here, the one that is small signal model for the BJT is the pi form, because it looks like the Greek alphabet letter pi. There is a pi resistance, and there's also an output resistance. And somewhere between the input port and the output port, but connected to the output, is a so-called dependent source. This source can be a dependent current source, or it can be a dependent voltage source. So in this example, this is a dependent current source. It has a transconductance GM. We'll see how this is calculated. And the input voltage, and that's the voltage that drops on this R pi. R pi is sometimes also indicated as R small e. And so what we do is we connect the voltage source to this small signal model, and then connect the output of the small signal model to the load. And so the dependent source here, GMBBE, could also be indicated as beta IB. It depends. It just depends which sort of a small signal model you want to use. And usually voltage amplifiers are cascaded. Cascaded means you amplify a voltage, but that amplification is not large enough. You amplify it again, and eventually you have an output stage. And so these different cascaded amplifiers we call stages. So the source here, the first stage in symbolic form, here it's a box, but here it's a stage. It has an input resistance, output resistance. The same goes for the second stage, third stage, fourth stage, and so on. And eventually you connect the load over here. But the input and output resistances in the symbolic representation have to be calculated. So the input resistances should be calculated looking from the source towards the first stage. The output resistances should be calculated looking from the load side inside backwards into the amplifier. And this has to be done for all these stages. So when we come to the second stage, for example, the source of this stage is basically the output resistance of the previous stage. Or the source of this stage is basically the amplified voltage plus the output resistance of the second stage. So if you want to find the total gain or amplification, we need to analyze all these stages separately. So if you if I want to give you an analogy, you want to live all alone in a beautiful tiny cottage, but you have no neighbors, nothing whatsoever. And you might need a dog or somebody, some animal to protect yourself if you're living in the middle of nowhere. But if you live in a community of houses, then you have neighbors. You can ask for help if you're sick. You can all share a pool. Well, not many of us have these individual townhouses, but this is just an example. So then I need to go over the so-called small signal, large signal. But before I do that, I want to give a little break. And that will last until 13:30. So a little less than, maybe just about 15 minutes. Is that all right? Now I can see the chat messages. Is that all right, guys?
It's all right.
All right, good. See you in about 15 minutes, and I will stop recording for this, but if you have any questions, you could ask. All right, I am back. Is everybody else back? Are all of you back? Are you back? Okay, good, good, good. Okay. Now we can continue. Again, share screen. We were left off with the large signal, small signal difference. Okay, what is a large signal? A large signal is the sum of the small signal and the biasing value. And the biasing value is always shown with capital letters. The small signal is always shown with small letters. The sum of them is shown with a small v, whatever the signal is, but large BE, for example, or CE. Or in terms of currents, large IB is the biasing value plus the small signal value. So we are working with biasing values at DC when we do biasing. And we work with small signals, and the sum of them is the large signal. What do we know? We first know that the collector current can be represented like this. Emitter current is collector current divided by alpha, which you remember was very close to 1. Or base current, IC divided by beta or HFE, and we know the beta ranges anywhere from, let's say in this class, 50 to about 300. And VC is, if it's VC, where is my, okay, VC, so that's basically the voltage that appears at the collector pin with respect to ground. In this case, it's VCE, and that is VCC minus RC, ICRC. We did that in the exercise session. And this particular circuit is a so-called common emitter design. There are 3 designs, and we are going to go over 2 of them today. So small signal values. First, IC is represented like this. If we want to find the large signal, then we need to add the small VBE over here. And since this is an exponential relationship, it's the multiplication of these 2. So the large signal IC is basically biasing value times the small signal. Okay. If that small signal is much, much larger than the thermal voltage, which is like 25 millivolts, much, much larger means at least 10 times larger. And that's true for small signals. Then we can put it in a series, this VBE divided by VT. And that's going to have a 1, then VBE divided by VT, then the square of it, third, and so on. And if we can neglect the rest, then the large signal is almost equal to IC1 plus VBE divided by VT. And this IC divided by VT, we call it transfer conductance. And it's represented by GM. So large signal is IC plus GM times this. And that is basically the small signal. So small signal values for IC, it's like that. And if you want to find IB, then we need to divide this by beta. And that turns out to be bias signal plus the small signal. So the small signal IB is transfer conductance divided by beta times VBE, or the little r pi is VBE divided by IB, and that turns out to be a value, HFE times RE, and this is we call HIE. What are these H's? These are called hybrid parameters of the small signal circuit. So the small signal pi model, for example, will be like this. The hybrid pi model. So the hybrid is why we use the H's. So the R pi, we learned it's HFE-RE. And GM, we learned it's IC divided by VT. So we can have it either in GM version or beta version. It's basically the same. For this class, that R0, which is not the output resistance, we neglected for the time being. It has to do with the early voltage. We'll remember this. So there are small signal T models also. So in the pi model, we had beta, the base, emitter, collector. Between base and emitter, we have our pi. Between collector and emitter, we have that dependent source. In the T models, we have a dependent source between collector and base, and only an RE, smaller resistance than HFE-RE between the base and the emitter. We also have an output resistance, but again, for now, we omit it. We assume it's very small. So therefore, this looks like a T, and we call them small signal T model. There are some model parameters. Of course, GM is IC divided by VT. RE is VT divided by IE. R pi is VT divided by IB. R0, as I said, depends on the early voltage, and its early voltage and the magnitude of early voltage. Remember, early voltage is negative, divided by the collector current. And we can have it in terms of GM or R pi, and the relationships between alpha and beta are like this. So what was early voltage? Early voltage is a reality because the output characteristic of the BJT, although ideally these had to be very parallel lines, it's not. It depends on VCE. But if we elongate these slopes all the way to the negative axis, they all get together and combine at the early voltage. And that's why the early voltage is negative. But for now, we are omitting the effects of the early voltage. The basic BJT amplifier configurations. This week, we are going to do the common emitter design and common collector design, or we call it emitter follower. What is the difference between them? In the common emitter design, and these are AC equivalent circuits. So there are no, in these circuits, there are no power supplies like VCC minus VEE and so on. This is the small signal circuit. We have the input from the base, the output from the collector. Or for common collector, we have the input from the base, output from the emitter. So collector is common between the input port and output port. And that's why it's called common collector. In the common emitter design, we have emitter between at the input port and emitter at the output port. That's why it's called common emitter. There's also a common base design. That means base is common between the input and the output. And in this one, we have the input from the emitter, the output from the collector. This we're going to do next week. So let's start with the common emitter amplifier at AC. That's the design. There's the input port, there's the output port. The input parameters are VBE and the base current. And it depends on VCE. Why does it depend on VCE? Because of the early voltage. Let's go back to early voltage. See, because of the VCE, the base current changes. So input characteristics have base current, the biasing base current, and biasing VBE, and they change as a function of VCE. We are going to omit VCE later on. In the output, we have VCE. Since the emitter is connected to the ground, this VC is also VCE, and collector current. And now the parameter is IB because IC is HFE times IB. All right. And then transfer characteristics. What are these? Base current, base emitter voltage, or collector current and base current. And of course, the parameter is VCE. Now, we need to look at some differentials. What does that mean? Again, the design. If VBE changes, it changes as a function of base current. It also changes as a function of collector emitter voltage. So if you put it in differential form, we take the partial differential of VBE with respect to IB at the operation point times DIB, the same for VBE and VCE at the point of operation times DVCE. We do the same first for the input port, then for the output port. And these are our so-called hybrid parameters. So how do we move from changes in DC to AC? Let's look at the input characteristics first. Instead of using dVBE, we can use delta VBE. If it's very, very small, and we use the small signal. The same for the base current, use a small signal. And the output, the same way. Okay. All right. Now, finally, a model. VBE is a function of these two terms. That's the input port. And these are the hybrid parameters I said. So the hybrid parameter, HIE, and that term is called HRE. The same for the output port. And now this is HFE. And if these two letters were capital, that was equal to beta. And in fact, for this class, we assume this is equal to beta. And that term that we call HOE. So if we look at these, voltage divided by current, so this has to be a resistance, HIE is a resistance. Current divided by voltage, this has to be a conductance. And voltage divided by voltage has no units, current divided by current has no units. Thus, HFE and HRE have no units. So the hybrid parameters, again, voltage is the sum of two voltages, current is the sum of two currents. So if you think in terms of Thevenin and Norton, obviously voltage is a sum of two voltages, HIE, IB, plus this. This is a dependent source. On the output part, we have HFE-IB. IB is an input parameter. VC is an output parameter. And for our purposes, we assume this is very, very large as a resistance or very, very small as a conductance. So it's open circuit. And if we can neglect the early voltage, then this small signal is reduced only a resistance at the input and a dependent source at the output. So if we have a circuit like this, from the video, you heard the capacitor behavior. So that's the source isolation capacitor. That's the load isolation capacitor. And this baby is a bridging capacitor. They are open at DC, shorted at AC. So when we look for the input resistance, we look from the right side of the capacitor. So we have the base dividing resistors, and then whatever is the small signal equivalent of this. But in that small signal, the emitter will be connected directly to ground, and the output resistance is found looking from the collector into that amplifier. So the common emitter design looks like this. The equivalent circuit at AC looks like that. So you see the capacitors have shorted resistors or have shorted to the output and the input source. VCC doesn't change with time. So it's basically ground. That's basically ground. So RB1 and RB2 come together between the base and the ground, and we have a parallel equivalent. And RC and R load come together at the output, so we have an equivalent resistor. So the common emitter design, when it looks like this, we apply a voltage to the base at AC, and at the output, we get another AC voltage that's amplified. But interestingly, they are 180 degrees out of phase. And that's why when we calculate gain in decibels, we need to use absolute values because they're out of phase. So that is where the negative comes from. Small signal circuit, insert it and use it. So now you know what this is. We basically omit the output resistance. That's a function of the early voltage. And GMVBE is equal to HFE-IB. So these are different ways of HFE is equal to beta. So these are different ways of symbolically showing the AC small signal. All right, that was the circuit. How does it look at AC? It looks exactly like this. The two come in parallel here. These two, they also come in parallel, but we need to find the output resistance between them. And we'll find these values. But since the emitter is connected to ground, these two are connected to ground, the input resistance is simply RB1 in parallel to RB2 parallel to R pi. On the other side, the output resistance is RC parallel to that R0, but since we omitted, the output resistance is basically RC. Okay? So how can we find the voltage dividing ratios? We find it basically from here. And how can we find the gain terms or what the output voltage is? Well, GM V pi, that's a current. And if we omit this, the current flows that way. And the current flows upwards instead of downwards. So from here comes the minus sign. And RC comes in parallel to RL. From here comes the RC in parallel to R0 and R0, we omit it. So the gain is basically minus GMV pi, which is basically this voltage over here, which is also V in. V in is the voltage over here, or VI. And that's as a function of the signal source, can be represented that way. And this is the output. So we first look at the output voltage, whatever drops here. And that's HFE IB or GMV pi times RL prime being RC in parallel to RL. VE, if there is a resistor connected to here, then the sum of these two currents will flow on it. So it's going to be RE 1 + 1 HFE IB. VI is equal to VB. That's equal to VB plus VBE plus VE. And so VBE is VB minus VE, then plus VE. So VI is basically VB. And what is VB? VB is the voltage drop on this R pi, which is HFE RE. And if we have a resistor connected here, the voltage drop on that one. All right. So we organize and assume HFE is much larger than 1. Then HFE plus 1 is equal to HFE. And we get a gain formula like this. V0 divided by VI is equal to V0, this term, that term, divided by that term. And all of them have HFEs. That cancels out with those and that. And all of a sudden, we end up with something that's simpler, and both terms, numerator and denominator, have IBs. That cancels each other out, and we end up with a term like this. So the gain is entirely determined by the resistors. Interesting? And what is RE? Well, RE is thermal voltage divided by the collector current, biasing collector current. And RI, what is RI? RI is basically the input resistance of the amplifier, and that's RB, which is the parallel equivalent of this, in parallel to RI prime, which is basically that one. And if we plug in the values, RI was found from dividing the input voltage by the input current. Input current going over here is IB. Input voltage, we had it over here or here. Both terms have IBs. From here, RI comes at HFE times that small resistance plus whatever resistance is here at AC, not DC. And therefore, it's not R capital E, but R small e. So, a recap, the gain is determined by the resistors, but for this resistor or resistance, we need to find the collector current. So we need to do the biasing. The input resistance is found from that formula. The output resistance is RC. Example. That example. Now you'll see what I mean by R small e. Because here part of the RE is shunted. So at AC, the emitter resistance is the sum of these two. So basically R capital E. But at AC, it's only RE. So these are the values that could be found with a T-type equivalent circuit. The result is the same. Do you have any questions this far? Because now I'm going to go over the common collector design. Any questions? And in the exams, for example, you need to know these formula only. And if we ask you to use small signal circuits, we will give you the small signal circuit. Okay? Now let's come to the common collector design. What is the difference between common emitter and common collector? The output in common emitter is from the collector. The output in common collector is from the emitter. That's the only difference. Okay, let's start. What is the small signal circuit look like? For AC purposes, VCC is 0. R1 comes in parallel with R2, exactly here. And that comes in parallel with R pi plus RE. If there is only one RE here, and there has to be RE because there is going to be a voltage drop on it. And I use beta IB or HFE IB. And again, this output resistance that is a function of the early voltage, we'll assume it's infinity. So this is not the collector here, or is it the collector? Let's look at here. Yes, this is the collector. If VCC is grounded, the collector is also grounded. Okay. So in a small signal analysis, we look at this circuit and try to find the values. What is V0? V0 is the voltage drop here. What is VI? VI is the voltage drop here. So, and it's funnily enough, VI is here, V0 is here, and somehow there is some voltage dividing. Okay. This value is going to be not much more larger than 1, but smaller than 1, not so small, very close to 1. Interesting, right? How do I find V0? Well, there's going to be a load resistor connected here, so it will come in parallel with RE. That's that term. And the current that would flow on the parallel equivalent is IB plus beta IB. That comes from here. And for the input voltage, we need to take account the voltage drop over here, and that's R pi times IB. So I put it as RE over here. With a little reorganization, it's very obvious that both have these terms, cancel each other out. And it's basically this. And when we look at it, it has actually not have a gain, but what is it used for? Let's first look at what the input resistance is. And that's basically the voltage drop on these two divided by the current. And that was this, divided by the current, IB, we get this term. So it's fairly large. Okay. Then there must be some trick with the output resistance. And for this, remember this is a circuit. We have to short the independent sources. So RS will come in parallel with these two. And add a current source or voltage source to the output. So R pi comes with RS. And actually I said something wrong. Wait. Okay. So, oops. The R1 and R2 are not taken into account in that case. So RS comes in parallel with R1 and R2, and it's basically RS shown as here. So they omit it. RS, R pi, or RE. Here is the base, there is the emitter, here is the collector. Collector is grounded. This is neglected. And that is the load. Okay, what do we do? Well, let's look at this node. Vx. What is Vx? The only way to find it is going over this way to ground. The current that flows over here is the sum of the base and collector currents. So it's IE. So it's basically minus REIE plus IBRS. The current over here is Vx divided by RL. Okay. So what is Vx? Vx going over this way is the sum of these two voltages, but with a minus sign, because IB flows in that way and it flows in that way. Okay, it looks pretty much like this, because why do I have HFE? Well, R pi is HFE RE. So that term RE times HFE comes from here. Okay, Vx is that. What is VB then? The voltage over here and the current over here. Well, it's Vx over here. If IB flows that way, then it's basically Vx divided by HFE plus 1 RE, which is R pi plus RS. Okay. Then what is Ix? Ix is basically this. We need to find it also other ways. The current over here is IE. The current over here is Vx divided by RL, right? So Ix can also be found from these nodes. Ix flows in, Vx flows out. What about IE? IE also flows in. So Ix can be shown like this. And IE, well, if we multiply this term with 1 plus HFE, that's IE. Okay. If we do this, then we end up with a current. That's the sum of two currents. That means if I divide Ix by Vx, I will find these two resistors in parallel. So that means R0, the output resistance of this amplifier, is the parallel equivalent of R capital E and the sum of RE plus RS divided by HFE. So this sum is fairly small because it's divided by HFE. That's then a small resistance, comes in parallel with a larger resistance. The parallel equivalent is going to be smaller than that resistance. So that means this amplifier has very low output resistance. Darlington configuration, I think we'll do this next week. We'll go directly into the exercise session. Beck, are you here?
I'm here, hocam.
Okay, please go on.
Okay, let me share the screen. Sorry. Can you see the screen right now?
We can.
Okay. Okay. Hello everyone. Today we are going to perform DC and AC analysis of this two-stage amplifier circuit. As you can see, first stage is common emitter amplifier because input is applied from the base and output is sensed at the collector terminal. Second stage is common collector topology because again input is applied from the base and output is taken from the emitter for this case. We are going to find biasing currents and small signal voltage gain, input and output resistance of the amplifier. These are the transistor parameters are given in the question. VA, early voltage is infinite. It means that small signal resistance of the BJTs are infinite as well, because this resistance value equals to VA is divided by IC. VA is infinite. It means output resistance of the BJTs are infinite as well. VT is the terminal voltage. It equals to 25 millivolt. VBE is 0.6 volt. HFE or beta or current gain 120 and IHRE or HOE equals to 0. We need to perform DC analysis to find biasing currents here. In DC analysis, all capacitors are open circuited. And look at the base terminal at the first stage. Two resistors are used to bias T1 transistor, and we need to create Thevenin equivalent circuit to make the analyze easier and simpler. Like small signal model, independent voltage source VCC is shorted to ground. Then that's why RBB Thevenin resistance equals to 67K3 parallel to 12K7, and it's approximately is 10.7K. What about the Thevenin voltage? Thevenin voltage is basically the open circuit voltage value. Here, the open circuit voltage equals to basically voltage divider. It's equals to 12.7K divided by total resistance value times VCC value. And it equals to 1.91 volt. We need to write a loop equation to follow the red line here. What is the VBB expression for the first stage? VBB equals to base current IB1 times RBB plus VBE plus emitter current, which is beta plus 1 times IB1 times emitter resistance, which is 2K. From that equation, as you can see, there is only one unknown variable here, a base current, IB1. It equals to 5.17 micron. What about the collector current of T1? It equals to beta times IB1, and numerical value is 0.62 milliamp. This is all for the first stage. What about the second stage? We are going to apply same procedure for second stage, and we are going to perform DC analysis. All capacitors are open circuits here. Again, we need to create Thevenin equivalent circuit. RBB equals to 15K parallel to 45K. It equals to 11.3K here. What about Thevenin voltage value? It equals to 45K divided by 60K times VCC value, which is 12 volt. Excuse me. Yes, 12 volt, and this Thevenin voltage value equals to 9 volt. We are going to write VBB expression. VBB equals to IB times RBB plus VBE plus emitter current times emitter resistance. this expression. From this expression, we are going to obtain IB2 as 41 microamp. Collector current of T2 equals to beta times IB2. It's equals to 4.92 milliamp. We found all DC current values for this two-stage amplifier. Now we can develop small signal model of the amplifier. In small signal analysis, an independent voltage source becomes a short circuit. That's why VCC is connected to ground in the small signal model. All capacitors are short circuit as well. That's why CC, CE, and other load capacitor CC short circuit here. As you can see, for the bridging capacitor CE is connected to emitter terminal of T1, and it will short the ground in small signal model. That's why there is no 2K resistor in the small signal equivalent circuit. Okay. Now we can find input resistance of the amplifier. Input resistance basically equals to Vs, input voltage, is divided by input current, In. It basically equals to RBB parallel to R pi 1. R pi 1 value can be calculated Vt over Ib. Vt is given in the question, terminal voltage. Ib is found in previous slide as performing DC analysis. Then we know the value of RBB1 and R pi 1, and it's calculated, it's 3.33K. This is the input resistance of the amplifier. What about input resistance of the second stage? We should find it because we are going to use it to find the voltage gain. As you can see, here is the second transistor's base node. We have two paths to calculate RI2. First one is RBB2. Second one is the resistance looking into the base of T2 BJT here. Let's call it RI2 star. What is the RI2 star? It equals to VB2 divided by IB2 value. Now we have to find VB2 expression. VB2 equals to IB2 times R pi 2 plus what is the equivalent resistance here? It equals basically 1.6K parallel to 250. What about the total current passing through this resistor? IB2 comes from here, then beta IB2 comes from the current dependent source. Total current beta plus 1 times IB2. Then this is the equivalent resistor. Then this is the VB2 expression. We are going to VB2 expression is divided by IB2 to find RI2 value. Then IB2s are cancelled out from the equation. R pi 2 plus beta plus 1 times 1.6K parallel to 250. And this value equals to RI2 star. It's 26.6K. What about the input resistance of the second stage? It equals to RBB2 parallel to R pi 2 star. Then RBB2 is calculated in the DC analysis. Then we know both value. Then RI2 obtained its value equals to 7.9K. Any questions so far? If you have any question, please write the chat box, or you can interrupt me. If not, I move on the small signal analysis of the amplifier. We are going to calculate voltage gain of the amplifier. This is the two-stage amplifier, and voltage gain can be calculated by multiplying stage gains with each other. As you can see, VO is divided by VS equals to VO over VB2. VO over VB2 is the gain stage of second stage gain, and VB2 divided by VS is the first stage gain. We need to find the output voltage expression here. Output voltage equals to total current flowing through this equivalent resistor. Total current here flowing into the ground equals to beta plus 1 times IB2 times equivalent resistor 1.6K parallel to 250K here. VO is divided by VB2 equals to this expression. VB2 is have already found in previous slide. Then from that expression, beta plus 1 IB2 cancel out here. Then simplified version of second stage gain equals to 1.6K parallel to 250 divided by RE2. RE2 equals to R pi divided by beta plus 1. This is the relation of between R pi and RE. Plus 1.6K divided parallel to 250. This is the second stage gain. What about the first stage gain? Vs source voltage can be expressed as IB1 times R pi 1. Now we need to find a VB2 expression, but in terms of IB1 for this time. How can we write it? We know the current dependent value here, beta IB1. What is the equivalent resistance that this current value has through? 10K here, and RI2 is the input resistance of the second stage here. Then 10K and RI2 parallel to each other. Then this is the equivalent resistor as well. VB2 equals to minus beta times IB1 times 10K parallel to RI2 here. Okay. And now we can combine with two stage gain. VO divided by VS equals to second stage gain times first stage gain here, and it equals to approximately minus 107 voltage gain. Okay. Any question? Okay. Now we are going to calculate output resistance of the amplifier. As you can see, second stage is a common collector amplifier. Unlike the common emitter type, using T model to find output resistance makes calculations simpler. Arrow is shown here, and as you can see, 250 load resistor is not included in the output resistance calculation. And source voltage, input voltage is set to 0. It means that beta IB1 will be 0 and beta times IB1 will be 0 for the calculation of output resistance. That's why this current dependent source is not included in the small signal model for the output resistance calculation. Okay, let's look at this small signal model. When we look from the output node, there are two paths. First one is lower path and its equivalent resistance 1.6K. Second one is upper path, and let's say its equivalent resistance of the upper path RO star. And let's define the current IO star. Okay, then RO star value equals to VO output voltage is divided by IO star value. And what is the overall output resistance of the amplifier? It equals to 1.6K parallel to RO star here. To find RO star, we need to express output voltage and IO star values or expression. What is the IO star here? As you can see, IB2 is coming from the base terminal beta IB2 coming from the ground here, then IO star equals to minus, because the current direction is reversed, minus beta plus 1 times IB2. Okay, this is the IO star. What about output voltage expression? Output voltage equals to IO star times RE2 plus minus IB2. Again, this is the current direction is reversed, minus IB2 times equivalent resistor of here. What is the equivalent resistor? 10K parallel to RBB2. Then the output voltage expression is divided by IO star, and it equals to this expression. My beta plus 1 times IB2 can be cancelled out here, then remains RE2 here, plus minus IB2 cancel out from the second term, then it's remain 10K parallel to RBB2 is divided by beta plus 1. RE2 can be calculated VT divided by emitter current of T2. Emitter current of T2 calculated in DC analysis. VT is given in the question, and beta is given in the question as well. We know the RBB2 value, then all parameters are known. Then RO star value equals to 48.9 ohm. What about the output resistance of the amplifier? It equals to 1.6 parallel to RO star, and it equals to 47.4 ohm. Okay. That's all for today, the problem session. Any question for the problem?
Yes, or for the class. No questions? No questions, guys? If no questions, then we'll see you next week, hopefully face to face. We still don't know. But thank you back. And I will see you next week. Goodbye.
İyi günler hocam.
İyi,
Haydi hepiniz hoşça kalın.
iyi günler hocam.
Sağ ol Berk.